Hi everyone, this is Mr. Lee. In this video, we're going to go over friction. All right, let's begin. So there are two types of friction, and the two types of friction is called static friction, and the other one is called kinetic friction. So it's important to note the root of these two types of friction. So static means that it is not moving. Okay, and so what we usually think about is like if you were to, I guess, like push an object across the floor or try to push it across the floor, but it doesn't move, it doesn't budge. That's because of this thing called static friction. Okay, kinetic friction is if you are pushing that same object, but it does move, it does budge. That's what we call kinetic friction. So usually, static friction, because it's not moving, your velocity initial and your velocity final is going to be 0 meters per second, right? And therefore your acceleration is going to be zero. So this is actually key. Kinetic friction, however, that just means that the force of friction is slowing down the object. Okay, and we'll go over the conceptual ideas as to why both of those happens. All right. So before we begin, the formula for both static and kinetic friction, the overall formula for friction is the force of friction is equal to this Greek letter. It's called mu. So mu, okay, times the normal force F of m. All right. Now, there's going to be different variations of this. So, for example, the force of friction kinetic, F of Fk, would be mu k times F of n. And force of friction static is a little bit unique, and we'll go into that uniqueness in a little bit. But I'm going to write the word max. Okay, so max force of friction static is equal to mu static times f of n. All right, and the reason why it's unique and the reason why I'm putting down the word max comes from actually what is happening within the scenario. All right, so I'll go over those scenarios and the conceptual ideas now. All right. So if I were to start off these notes, I would ask you, we need to be able to come up with an image in our brains of what's happening when friction exists between two objects. So hopefully right now you're like sitting on a desk, right? You're not like falling through the air. If you take your hand and you put it on top of your desk and you rub your hand back and forth, okay, you should feel a little bit of resistance. Now, it's just a quick review. If your hand is able to slide back and forth over the desk, that's called kinetic friction, right? Because it's your hand is moving. But if you were to put your hand on the desk and you if you're trying to move it back and forth, but your hand's kind of like stuck there, right? So instead of doing this, like your hand is there and it's just like not budging. That's what we call static friction. And the reason why friction exists, I'm going to give you two different kinds of images. So the overall image is the following. Let's say here we have the table, and instead of your hand, let's use a different object. Let's say a book, right? So this is what we call the macro view. So in the macro view, or like the view that we see with our eyeballs, okay, this is what we see. We see a book on top of a table. But if we were to zoom in right here, okay, like really, really zoom in there, this is what we would see. Okay, so we would see from the book. Okay, if we were to really, really zoom in using like a superpowered microscope, we would see the surface of the book not look smooth, but look actually like pretty jagged, like this. Okay, so this is a zoomed in view of the book. And even though like to our eyes, the book might look smooth, if we zoom in, zoom in, zoom in, there's gonna be like dents and like imperfections within the surface. And that's what causes the book to have those like mountains and like those ridges and those like valleys. And the same holds true for the table. Okay, so I'm gonna draw the zoomed in view like down here, right? Like this. All right, so this is the table. Now, in this case here, I made it so that the book and the table, they're not touching. But in reality, the surface of the book and the surface of the table are in fact touching. And when the top surface, the book, touches the bottom surface, the table, a very unique thing happens. The mountains and the ridges sort of like interlock with each other. And so when there's like interlocking in class, like if I'm trying to explain the scenario for you, I'll often do this with my hands. And so I would love it if you can do it with me. So your top hand, okay, the fingers pointing down, this is the jagged mountains and the ridges of the book. And down here, this is the mountains and the ridges of that table. So to our human eyes, okay, the table looks smooth, but for it to zoom in, right, we have these mountaintops. Okay, so I'm actually going to do it like this. Now, when the book and the table are on top of each other, okay, so this is the book, this is the table, I'm going to make the book and the table on top of each other. Okay, this happens. So the mountaintops and the ridges, they sort of like lock in place. Okay, and so when it's locked in place, if I try to move the book back and forth, okay, we can see that the book doesn't really move. And so because it's not moving, this is what it looks like if we were to zoom in using like a microscope. This is what it will look like conceptually for static friction. Okay, so static friction is when your two surfaces lock into place and there's no budging. Okay, there's no budging right there. Now, the idea of kinetic friction is, let's say you are strong enough to move the book across, right? So instead of being like perfectly locked in place, it's like sort of locked in place, and like you push it hard enough so that your fingers like can like not be locked in place, and so it just kind of like juts up and moves across. And so when that happens, okay, so I want you to do it like this. This is what kinetic friction looks like. So kinetic friction is when these surfaces are moving on top of each other like this. And so instead of being locked into place, which is static, kinetic, it's like the two surfaces are rubbing against each other like so. All right. And so because it's not locked, there's motion that's allowed to be happen. And because there's motion that's allowed to be happen, we call that kinetic friction. Okay. Now, for kinetic friction, right, as the two surfaces are being rubbed against each other, um, the reason why it slows down is it's like kind of like imagining like driving over like speed bumps, okay, or like if you're like trying to run in the hallway and you're just constantly running into things. So as you're running in the hallway and you're running into things, you're going to inevitably be slowed down every time you make a collision. So for kinetic friction, right, if this is my book and this is my table, okay, so do this with me, book, table, when your fingers rub against each other, okay, some of that velocity is slowed down because there's collisions happening. So the reason why friction slows objects down are due to these atomic or microscopic collisions. Okay, so if we were to do a quick conceptual check, all right, so for static, there is a quote locked surfaces. Okay, so they're like locked into place like that, and they do not move. So your velocity is going to be zero no matter what. And for kinetic, the surfaces are bumping into each other. Okay, so because the surfaces are bumping into each other, this is the thing that causes the slowing down. Now, the cool thing is that as the two objects are rubbing against each other, which is kinetic, after a while, okay, when the object is slowing down, there's going to be like a time when it can't move anymore, and then the force of gravity will just like make it so that the two surfaces just kind of lock in place. So you go from a kinetic friction to a static, right? And that static friction occurs when, right, there's no more motion that is really happening. Okay, so you're no longer moving. All right. So with that out of the way, let's take a look at scenarios for static friction. Okay, because that's where things get a little bit unique. We're just going to do a couple of quick examples. So if we were to have an object here, we know that there is f of n, so that is the surface pushing up. So imagine that there's the ridges there as well, and we have fg going down, right? And if we were to push this object to the right with the force of 2 newtons, okay, the force of friction, right? So if this is a static situation, there has to be a force of friction that is pointing to the left. Okay, so now the question is, how strong must that force of friction static be in order to prevent this scenario from moving? And so we know that if we're pushing it to the right of 2 and we are in equilibrium, the force of friction static must be equal to 2 newtons. Okay, now same idea, but let's say we push it a little bit harder. Okay, we push it a little bit harder, but even if we push it a little bit harder, the object still doesn't move. Okay, so same scenario, we're just pushing it a little bit harder, so it still doesn't move. So if it's still not moving, okay, we must be in equilibrium. And if we're in equilibrium, the force of friction static must be equivalent to however hard you're pushing, 3. Right? And then like we can continue with these examples. But the big idea here is when I say that there is a max static friction, what that means is that you're pushing on the object or the two surfaces are going to be locked. But if you push, right, those surfaces are trying to unlock from each other. And there's going to be a tipping point for when the surfaces can only hold on to each other for so long. And at that point, we go from static to kinetic. Right? At that point, we start to move. And so when we say max static friction, the graph kind of looks like this, right? So here, this is like zero force, right? So this is my force applied. So it's let's say F push, and we can say that this is like F of F. So if we increase the push, okay, the force of friction static, it matches it. Okay, we increase the push, the force of friction static matches it, and we just do it this one more time. We increase the push, and the force of friction static matches it, right? And then we're going to push just one last time, but this is like the tipping point for where the mountains and the ridges are about to break apart, okay? And so when we push it one last time so that it does break apart, okay, right here, this is what we call F of Fs max. So at that point, at max static friction, okay, we go from a static scenario and we jump straight to kinetic. Now, there's a unique thing that happens because the interlocking surfaces are not able to hold on to each other, okay, but just like brush against each other. Kinetic friction actually is lower than the force of friction static, okay? And the unique thing about this is that F of Fk is a constant. Okay, and so with this idea, okay, there's a little drop that happens when you go from static to kinetic. And so force of friction static max will always be greater than force of friction kinetic. Okay, but the unique thing here is that the force of friction kinetic will always be constant. Okay, it doesn't adjust according to how hard you push. And so what that might look like, it will look something like this, right? So f of n, f of g, and let's say you're pushing with, let's say 100 newtons, but our force of friction kinetic would be, let's say 80 newtons. So here, what this shows you is that your net force along the x-axis would be 20 newtons. So we're still accelerating because we were able to unlock those surfaces. But let's say we push even harder, right? And we push instead of with 100 newtons, we're now pushing with, let's say, 200 newtons. If I were to ask you, what would the force of friction kinetic be? Okay, the answer should be still 80, because that doesn't change. This is a constant. So you can see the things that you have to keep straight in your mind is what is the force that's adjusting to the scenario, and what is the force that never changes, all right? And so the big idea is static will always put us in an equilibrium situation. So that's one way of memorizing it, or you could just memorize that the force of friction kinetic will always be the same. All right, cool. So let's go into what the different parts of the formula tells us. So if we take a look at the force of friction formula, okay, the general one, we have mu times F of n. So what mu tells us is the coefficient of friction. And so another way to think about this coefficient of friction is I guess, the ratio of how, I'm going to put this also, this quote in quotes, locked the ridges are. Okay, so what this means is, let's say you have like a more or less like a more frictionless environment, such as ice. So if I were to do like a zoomed in view, right, of like carpet, so carpet, like a very zoomed in view of carpet would look like this, like a lot of ridges, okay, a lot of ridges. So like if you like slide across that carpet, you would definitely get like carpet burn because all of those ridges are just like ripping into your skin. Versus a zoomed in view of ice, ice would look maybe like this. Okay, so not as many ridges. So it's, when I say it's a ratio, it has to be between two objects. So if we were to slide like a textbook, so this is like carpet, and this is ice, right? And I'm going to just draw the textbook right here. All right, so this is my textbook. So if I were to run this textbook over this carpet, because the carpet and the textbook have a lot more ridges to brush against, the mu is high. Okay, so the ratio of the interlocking ridges is really, really high. Versus if we were to rub this textbook surface, right, those mountains and those ridges across this ice, there's not a lot of collisions that occur. Okay, so because there's not a lot of collisions that occur, your mu is low. Okay, meaning that there's not a lot of grip, quote unquote, grip between the surfaces. Okay, so another way to think about it is if your mu is big. Okay, I'm going to put this in quotes because I don't like really using this word, but I think it really does help us remember it. The grip is high. And the reason why I don't like using the word grip is a lot of times students think about like their shoes, right? So if you look at your shoes, you can visually see like the ridges, right? Not the same, right? So everything here in terms of frictions is like very zoomed in, like on the atomic scale. If your mu is low, okay, the grip, there's like less grip, or this is more of a frictionless environment. Friction dash less. There's less friction. So, but if your mu is 0, this is where you have your f of f to be 0, right? And so that's why a frictionless environment is very theoretical, because every single surface has mountains and ridges just because of imperfections in any surfaces. So when we do our problems, we like to think about it in a very theoretical sense. And so when we say ignore friction or friction doesn't exist, okay, the reason we have to state that is because in the real world, friction actually does exist. Okay, and so this is a purely theoretical situation. Theoretical. All right. So we just covered what mu represents, and let's cover what f of n represents. So f of n is the normal force. Okay, so we already know that. Now, the reason why normal force is in the problem is, well, let's just do a quick little concept check. Okay, so let's say this is I don't know, this is like your table, and this here is, all right, there we go. This is your textbook. Okay, I think it might be easier to do with my fingers. So we have the table and we have the textbook. So right here, the table doesn't have to really support the textbook as much, and we can only see that by comparison. If we were to increase the f of n by pushing the textbook into the table, right? See what happens here, right? My fingers become even more interlocked. So if we were to get a textbook and we were to push the textbook into the table, what you're essentially doing on the zoomed in scale is you're forcing the ridges to interlock with each other. And so if we take a look at the formula, we can now see, right? So if you force the surfaces to interlock by like pushing the two objects into each other, your F of n will increase. So if your F of n increases, your force of friction will increase. Um, all that with saying that the two surfaces, we're not changing the mu there. Okay, so they're directly proportional to each other. And on the flip side, right? So if this is what your surfaces look like, okay, if we were to decrease F of n by like lifting the object off of the table ever so slightly, my ridges will come apart. Okay, so if my ridges come apart, there's going to be less friction. Right? So a very interlocked system is a high friction, and a less interlocked system is a lower friction. Okay, so we just covered everything that there is for friction. See you next time. Bye bye.